Sometimes the Abaqus element library won't be enough, and you need new element type. So how do you plan to solve this issue? Well, the answer is UEL subroutine. Watch this video to learn how to use this sophisticated subroutine.
In the current package, we will work on learning how to write a UEL subroutine in Abaqus. Let's take a look at what you will learn. In the first section, we will discuss when you need to use UEL subroutine and how this subroutine works. And then in section 2, you will get familiar with UEL subroutine interface. Variables, either to be defined optional ones or which are inputs to the SR. Also, all notes required on how writing a UEL will be explained in details. Finally, various workshops on how implementing UEL are presented. In these workshops, we start from formulation and then explain required settings in Abaqus CAE and .inp file. Next, we go through the sample subroutine line by line to show you how to write it in Fortran. To begin, you should know when to use this subroutine. When you cannot find any appropriate element matching your formulation in Abaqus standard element library, UEL is the answer. Remember that sometimes there is no need to write UEL and much simpler subroutine, deload, can be used. When defining very complex loading conditions, if the load is deformation dependent, we require a UEL subroutine. To show you how this subroutine works, imagine that the analysis starts from an increment. And Abaqus have calculated field variables when an iteration starts. In a most general state, UEL can account for calculating strain increment, calculating stress and Jacobian, and also defining loads of the solving process, plus other subroutines related to these stages, such as UMAT, can be called by UEL. As you can see, any of these subroutines, just consider one of the stages, like UMAT here, or deload and film, which are used for defining loads. When an iteration starts, you need to find elements stiffness matrix. Then you should define loads. And after that, equilibrium equation is solved, where K is element stiffness, C includes elements DOFs, and R represents loading. And lastly, Abaqus checks for convergence of that equation. In practice, UEL is mostly used to define KEL and in some cases to define loading. Note that we can use several UELs at the same time. You just need to write all of them in a single Fortran.4 file. As stated before, if material behavior is such a complex one that is not supported by Abaqus material models, you can use a UMAT and call for that inside UEL coding. In a UEL subroutine, element stiffness matrix is calculated based on this relation. That is the derivative of F in respect to the variation of DOFs. We will speak more about this in the following slides. I remind that K is element stiffness or Jacobian matrix. H includes state variables that may optionally be defined and used by user, and DU consider the changes in DOF's values. Now we will see how we could refer to Abaqus documentation to get needed information about UEL subroutine. When you open the Abaqus documentation, go to the reference section and select Abaqus user subroutines reference manual. After entering the manual, since the solver for UMAT is Abaqus standard, at Abaqus standard subroutine subsection, look for UEL. As you can see in the interface part of the UEL page, there is a template that you should follow exactly when you're coding. You must just write your own code instead of the user coding for defining line. Another important part of the manual is about different variables that are accessible in a UEL subroutine.
Now let's see how to use this subroutine in a very simple example. First, let's explain the problem.
In this section of the video, we try to write simple UEL subroutine and implement it in Abaqus. In this workshop, element beam with nonlinear behavior has been modeled with UEL subroutine. As you can see in the description of the problem, coupling between actual and bending term has been applied on the model. This behavior is like as using beam general section with nonlinear general option. It should be noted the element has two nodes with two Gauss points. Two A and B nodes have 3 degrees of freedoms. There are 2 translations and 1 rotation degrees of freedom. To add nonlinear behavior to the beam, we add node C in the middle of the beam element. This node has only tangential displacement degree of freedom. We can calculate the tangential and vertical displacement in Gauss point via shown equations. By using displacement of A, B, and C nodes, in calculation of tangential displacement in Gauss points, tangential degrees of freedom of 3 nodes has been used. However, vertical and rotational degree of freedom of A and B have been used to calculate the vertical displacement. Pay attention that L is element length, zeta is dimensional position along the beam, which is calculated based on S divided 2 element length. We can calculate the strain and curvature using the first derivative of tangential displacement and the second derivative of the normal displacement of the beam. We want to describe more about used theory in this workshop. B matrix can be obtained from the following equations. In fact, B matrix is calculated by arranging the equations in previous slides. In this arrangement, degrees of freedom are separated as a vector, so the remaining part will be the B matrix.
Okay, let's see how to solve this problem using the UEL subroutine.
1 node number, 2 first coordinate of the node, 3 second coordinate of the node. Star element will be used to define elements by giving their nodes. Data lines to define the elements are element number, first node number forming the element, second node number forming the element. Then element set and node set have been defined. Details of defining these sets are described as follows. In star EL set command, elements have been assigned to an element set. Note that data lines are as follows. If the generate parameter is omitted, first line is list of elements or element set labels to be assigned to this element set only previously defined. Element sets can be assigned to another element set. However, data lines, if the generate parameter is included, first value is first element in set, and second value is last element in set. Last one is increment in element numbers between elements in the set, and the default is 1. In this line, beam section will be defined. This option is used to define the cross-section for beam elements when numerical integration over the section is required. In this command line, element set, material name, a mode of temperature, and the name of the section type will be defined respectively. Then beam section geometric data, length and width of box section will be defined in first line. And in the second data line, first, second, and third direction cosine of the first beam section axis will be defined. The entries on the second data line must be 0, 0, -1 for planar beams. Pay attention to apply this feature. You need to assign beam section orientation in property module as follows. Then, end part command is used to end a part definition. Star assembly is used to begin an assembly definition. Name parameter is equal to a label that will be used to refer to the instance. Part parameter is equal to the name of the part being instanced. Finally, we end the definition of an instance with this command. After that, the star material is used to indicate the star of a material definition. Name is equal to label that will be used to refer to the material in the element property option. This deep var option is not necessary because we use UEL, not user material. We specify elastic material properties with star elastic. The Young modulus and Poisson's ratio are entered in this line respectively. Star step is used to begin each step definition. Name is equal to a label that will be used to refer to the step on the output database. NLGeom equal yes indicate that geometric nonlinearity should be accounted during the step. Star static is used to indicate that the step should be analyzed as a static load step. The data line for this step are initial time, increment, time period of a step, minimum time increment, a load, and maximum time increment, a load. Star boundary is used to prescribe boundary conditions. Then all degrees of freedom in Caster are applied to node set label set 1. Star C load is used to apply concentrated force at the node set or set 2. In direction y2, its magnitude is equal to -1 Newton. There are amounts entered in line 73 respectively. Star restart is used to save and reuse data and analysis results. Write is used to specify that restart data are to be written during the analysis. When restart is required in an analysis, restart information is always written at the end of the step. Set frequency equal to 0 to discontinue the writing of restart data. Star node output is used to define output database requests for nodal data. They are CF, a concentrated force, RF, reaction force, and U displacement. Star element output is used to define output database requests for element variables. They are LE, or logarithmic strain, PE, plastic strain, PEQ, equivalent plastic strain, PE mag, plastic strain magnitude, S, stress. Star contact output is used to specify contact variables to be written to the output database. Finally, we have star output history to define output requests to the output database, and with star end step, step definition is finished. To prepare input file for UEL subroutine, it is necessary to copy the input file title job 1 firstly. The changes are required in previous input file will have been highlighted. These lines should be entered before section definition part in input file. Star user element is used to introduce a user defined element type. Key used to identify this element on the star element option. The format of this type key must be UN in Abaqus standard. When n is a positive integer less than 10,000, star nodes is equal to the number of nodes, 3 associated with an element of this type. Coordinate is equal to activated degrees of freedom of the user elements 2, which are in x and y direction. Properties is equal to the number of real floating point property values 3 needed as a data in UEL subroutine. Variables is a parameter equal to the number of solution-dependent state variables that must be stored within the element. Its value must be greater than 0. The default is 1 for variables. As I mentioned in presentation, in the first line, the list of active degrees of freedom at the first node of the element are defined, which are 1 x direction, 2 y direction, and 6 rotation about z-axis. In the second line, the active degrees of freedom are different as subsequent nodes are entered. Firstly, the node number 3 and then the list of active degrees of freedom are entered 1. After that, star element with type equal U1 is used to assign user element to specified elements. This element is named as EL set equal to 1. In data line, we specify element number 1, which the connectivity nodes are 1, 2, and 3 for this type of element. Pay attention, node number 3 is the middle node in user element. As can be seen in line 30, it has different degrees of freedom. 1 only, 1 and 2 node numbers are nodes of 2 beam ends. Star UEL property is used to define property values to be used with a user element type. EL set is equal to the name of the element set containing the user elements for which these property values are being defined. The numbers of UEL properties are 3 as defined in line 28 in properties equal to 3. These values or props have been defined in subroutine. As you can see, they are height, width, and Young modulus respectively. To run the model with written subroutine, you should create job and select job1.inp as source. Then attach the UEL subroutine and submit it to Abaqus standard solver to solve it via Abaqus. We submitted the job in advance. We are going to see the result and compare it with Abaqus model without user element. If you select the result from this module, you can see different results like stress, strain, and so on. The hidden element is user element. The actual force and moment for UEL subroutine could be seen in log file, because we have written some printed commands for them in the subroutine. You can see displacement, reaction force, and reaction moment for user elements as follows. To compare result of Abaqus model and subroutine, you need to create viewport and tile them vertically as follows. The difference between stress for two models is related to hidden element, user element, which visualization module does not show that. Contour of reaction forces are completely same because this result depends on node, not element. In addition, concentrated forces are same between two models. Stress result for the second element, visible element, has been compared with each other. As you can see, stress are approximately same. The difference is related to using different element, user element, with 3 nodes and nonlinear section behavior. We describe more about the subroutine and how to get result in next workshops. So we have simulated the beam with 2 different elements, one of them using user element and the other one using Abaqus element type. Then we have compared this model with model which has been used. Abaqus element type completely. Finally, we compare results and find out good agreement between them. The difference between results are related to use the specific element which can implement nonlinear section behavior. It should be mentioned we have got some result for actual force and moment in log file. I hope you have used this workshop enough.
Let's see another example. Beam element with specific boundary conditions and loading.
In this workshop, we are implementing UEL subroutine for a beam element with specific boundary conditions and loading. In this workshop, an example is calculated using the analytical method and a FEM user-defined subroutine method to verify results. Element type used for the analysis is Abaqus B21 element. The figure shows an Euler-Bernoulli beam element. The element contains two nodes. Nodes 1 and 2 are located at the end of the element, and nodal variables are the transverse displacement V1 and rotation θ1. Thus, each node has 2 degrees of freedom. We can show degrees of freedom with Q vector. For convenient, we use Q1, Q2, Q3, Q4 to denote V1, θ1, V2 and θ2. Shape functions for this element are written like equation 2 when it has vertical motion, which h1 and h4 are defined according to equation 1. Zeta is the coordinate of integral point like previous workshop is s divided to L. According to equation 3, x can be function of x1, x2 and zeta. The length of the element will be differences between x2 and x1. Equation 4 derived from the derivative of above equations with respect to x direction. Here we can multiply H matrix by Q, which is degree of freedom. The H matrix corresponds to this equation. Now we can write the potential energy equation for the element. We have energy equation according to first statement of the equation 5. Equation 6 will be obtained in the first equation by placing sigma and epsilon, which are stress and strain respectively. So we have equation 7 as follows. We could use I, moment of inertia, instead of integral expression in equation 6. According to equation 8, which are stress in bending mode, strain and deflection, we have equation 9. Therefore, the internal energy equation of the element is according to equation 10. Equation 11 will be created by substituting the second statement with the first statement of equation 10. The second derivative of h with respect to zeta corresponds to this expression. Okay, you can see the result by selecting result. As you can see, result for 11 nodes, 10 elements are visible. To compare result between Abaqus and subroutine, you need to create viewport and tile vertically their viewport. As you can see, the stress results are not visible for subroutine model. As I mentioned before, these results are stored in stress.dat file. We want to compare different variables like moment, shear force, and stress in point A between FEM using subroutine and analytical solution. After final next step, text the results for element number 1 including point A is visible. Bending stress for node number 1 and 2 are minus 347.2 and 187.5 respectively. As you can see in the slide of presentation, all results including stress, moment of, and force are completely same as analytical results. Yes, these are moment and force in point A in stress.dat file using UEL subroutine in FEM solution method. This is a good agreement between results in two different methods. We can also compare the result between using Abaqus model and subroutine model in visualization module. As it is visible, reaction force contours and amounts for Abaqus and subroutine models are same. We can also compare the reaction force in point A between Abaqus element and subroutine model as follows by using props value tool. It is also possible to compare the deflections between two models. For example, the displacement magnitude for node number 6 is approximately same. This is also show good agreement between Abaqus element model and using UEL subroutine. So we compare three results including Abaqus element, UEL subroutine, and analytical solution with each other. They show us the written UEL subroutine works well. I hope this workshop could help you to learn how to use this type of subroutine and could help you to write your customized subroutine for your project.
Hello everybody and welcome to our new video training package of Abaqus UEL subroutine in Abaqus. This package includes these sections: Introduction to UEL subroutine in Abaqus Workshop 1. Writing UEL subroutine for planar beam element with nonlinear section behavior. Workshop 2. Beam element with specific boundary conditions and loading. Thank you for taking the time to watch this video. We hope it will be useful for you.